If you have any issues, let us know. If we can help, we will be more than happy to help. And I'm pretty sure there are going to be little challenges here and there with the coding, Python, and so on. That's why we are here, okay? Of course, feel free to talk to your classmates. They're going to probably help you more than us, but we are here to help, all right? Ogerta will go next, and then...
So hello everyone, so I'm Ogerta and I'm an associate professor in applied AI in Birmingham City University. Before moving to UK 4 years ago, I have been working as a lecturer in the University of Tirana, Faculty of Economy, where I was graduated, and before being part of academia, I have been working for 10 years in the National Office of Statistics in Albania, where I have been leading the IT and methodology department. So I have a background of 10 years working in industry, let's say, and 10 years in academia. In the university, I'm involved in teaching different modules, computer programming in Python, with social media analytics and visualization with NLP, and also modern data stores. This is what I teach, and also I'm involved in doing research, and my research recently spent in applied AI in different domains, but I've been involved in some projects with Innovate UK and some big companies in UK in how we can adapt generative AI in the construction domain. This has been some of the projects that I've been working recently, and yeah, today with Zoe, we are going to go through the course, and yeah.
So, I guess challenge number one, I guess that everybody has received an email from Dr. Elazin with the class link, right? Okay, and then probably all of you, or most of you, have registered for the course, and you are able to actually see this Google Classroom. Yes? Okay, good. So initially we're going to go through a little bit the class structure and what we are planning to do here those 5 days. I mentioned in the event this morning that the schedule is not very strict, okay? Because I know that we are coming from different backgrounds, so a couple of you may have coding issues, a couple of you may have fundamental issues with math and so on. So we are here mainly to help you understand what you need, okay? And we may postpone, we may delay a couple of things from the material just to make sure that you all understand, okay, what is happening. This course traditionally is like a course that is taught for one semester, 15 weeks, 14, 15 weeks, okay? What we have tried here to do is we tried to actually compress this material to 5 days. So, don't get scared today if you see something that you don't get. That's why, again, we are here to help you get it. Okay? Tomorrow it's going to be a completely different day. We're going to move to something that is more advanced than what you will see today. But there is a smooth transition. And we tried to actually cover the evolution of deep neural networks and tried this evolution to just, again, compress it within 5 days. All right, so if you all go to the classroom, you will be able to see the classwork and the way we have set it up. So, again, you know that there are two sessions. Session 1, Session 2. Session 1 is in the morning, Session 2 is later on. Here, in the Google Classroom, Session 1 is all about the lecture. Is all the slides that we are trying to present. Okay? Now, there are a couple of slides that we will not have time to go through. However, you are more than welcome to take them home, read them at a different stage. And again, remember, this is an evolving learning curve. You don't get it today, you may be able to get it in a month, all right? So that's why you will have access to all of those notes for you to educate yourself and get better and better and better. You see here that we have the morning session 2, and I call it coding labs, which is technically all the code, the Jupyter notebooks, that reflect the material of the day that we are. So for example, today we're gonna go through the fundamentals. The coding lab will be on the fundamentals. So we're gonna build our first neural network and we're going to do handwritten digit recognition. Okay? Same happens for every day. Tomorrow it's gonna be convolutional neural networks, same for the lab. Now, we have also assignments. And I know that, or I already have received a couple of questions about how do you determine in the assignments what's going to happen. So the assignments are very, I would say, unofficial. So we have prepared for each day 10 questions, multiple choice, that you should answer. And we're going to give you a couple of minutes, like 15 minutes, to answer those after we present the material. Now, after you try, after your attempt, we're gonna go through again together. Okay? You're gonna receive a grade, but do not look at the grade. Do not worry, you won't fail this. Okay? The grade is happening because Google Classroom sets it up. All right? In addition, we have a project that is a different project from the hackathon that's gonna happen. I don't remember which day, someday. Okay? The class project is going to be on neural network, and it's going to be on something that is very challenging in the field of natural language processing, or NLP. It's on translation, okay? And since we are in Albania, the task will be to take a couple of Albanian articles, translate them, and see whether or not a deep neural network understands English better than Albanian. Okay, and vice versa. And then from there, we're going to build a classification model. Now, you are more than welcome to start the project today. And if you want guidance, we're here to help. But what we are planning to do is to spend those first 2 days with material. And the third day, we're going to start discussing the project in the class. Okay? So we hope that Friday, which is the last day, you will be able to actually submit something, okay, as a project. Now, the project is a project that cannot be done using solo ChatGPT or Claude. Even if you do, probably you won't be able to understand all the fragments of code that ChatGPT will give you. And this has been intentional. The idea here is that use ChatGPT, use your favorite LLM model to generate code, but at the same time, you should be able to understand what the code means. Okay? And not only the code means. I don't want you to go character by character. I want you mainly to understand what the output means. And how do you make the framework or the pipeline better to improve the results. Okay? You will see that in the project there are many different aspects, starting from the very basics like tokenizing Albanian words to translating Albanian words. All of those are hard problems to solve. Okay? And do not expect that ChatGPT will solve it for you. Again, here we're gonna do it together. And I'm pretty sure you will all enjoy and you will succeed. For the project, you can be in teams. You submit only individual. You can work with your friends. You can work with anybody. You can work with your favorite LLM as your teammate. And then you submit one single project. Again, the grade is unrelated. You will all pass, okay? We're gonna say, but I'm gonna say it today. The project is like a project that has been assigned to a company. Okay? You will feel that you're gonna be like a data engineer or an AI engineer in a company who needs to solve a problem. So your task won't be to just code something. It's not an assignment. Your goal will be to set it up from the beginning. And trust me, the challenge when you are working with such big projects is not how to actually write 10 lines of code to execute something. The challenge is to set it up, okay? And know what each component of a big pipeline does for you. That is going to be the main challenge, but this is what we're going to discuss. All right? Now, as with all companies, the project won't be successful. Do not expect to get 99% accuracy, okay? But you will expect to get initial results to demonstrate to your colleagues, to your hiring manager, to your product manager, all right? And from there, later on, you can work even more on this. You can post it on your GitHub page, build up your portfolio, and get ready for your career, all right? Let me see if I have anything else. Yes. I don't have anything else to say, and you have a question.
Yes, just to get it straight. Is if there are going to be two projects, one for the hackathon, and this is only for the course, or?
Yes. So this is, the course has its own project. The hackathon is something completely different. Okay. So I learned today that there is a hackathon. I didn't know that there is a hackathon. So this is just a class project, all right, which is no competition, nothing. We just complete it to learn, all right? Good. Other questions? Gerta, you want to say something?
Something about the quizzes. Did you mention the online quizzes?
Yes. So the quizzes again. After we go through the material, you will get 15 minutes, do the quizzes, and then we're gonna discuss them together. All right? Other questions? Yes.
I went through the project yesterday, and I saw that there were like 35,000 articles to choose from.
Good.
So, and it takes a lot of time to translate. So will
Okay.
you be using all of them, or?
Okay, I'll answer what you. This is an excellent question. So someone went to the link and clicked on it and saw what is happening. So this is the real project, and this is the reality. In a real project, you won't work with 10,000 articles. You will work with millions of articles, and the task will be to actually translate. Why you gonna fail the first pass? Simply because you won't have memory in your machine to translate. Translation is one of the most challenging problems in NLP. So I didn't intentionally in the project description, we didn't say how do you attack this challenge, because we want you to think how to deal with this issue. This is where you're going to get your data set from. Yeah, so the data set is like a couple of.
Yeah, but you can use it for coding.
You can use it for coding. So if you work in a company, no one will tell you do not use ChatGPT or this or that or the other. You are free to use whatever you feel is useful for you to solve it. So here we want you to solve a problem, a real world problem, or attempt a real world problem. I'm pretty sure we won't solve it, because if we solve it, then next year we won't be here, right? So feel free to use anything. Good? And day 3, we're gonna start releasing code about the project, and we're gonna start making suggestions. How do you deal with this massive data set? Just to give you a hint, we won't deal with 35 million articles. We will go much less, just for demonstration purposes, because you do not need to demonstrate this idea. You do not need this much data. All right? Any other question?
I would just like to add that the reason that we have included the full data set is because we want to think you about the real problems, let's say real challenges in the industry, how it works. The data sets are really big, and even in this case, you have all the data set, and most probably maybe you will not be able even to download because it takes a lot of time and so on. But you have to think about, okay, I can't use due to lack of resources and the computers that you are using, and you cannot use the whole corpus of data that you have, but you have to select part of it, or what we call it sample selection. And you have to think about the strategy, which articles you want to select. and it will be a problem of classification, and there will be articles belonging to different classes. What does that mean? Should I select the same number of articles belonging to each class, or should I have a balanced data set, or should I have an unbalanced one? And if I have an unbalanced one, how I have to tackle this and so on. This is really important. It's not about getting the data and sitting down and just writing lines of code in Python. When it comes to data science projects that we work with industry and so on, around 80% of the time we spend with data pre-processing, let's say, and only 20% we spend with analysis and deploying and running different models and so on. And this is an important task, and that's the reason that all the data set is available to you. But as Zois mentioned, so starting from week 3, so day 3, sorry, not week, we'll provide to you also escalation of code that you can reuse it and you can rerun it, and the focus it will not be to learn Python or to test how good you are in Python and so on. You can use any of large language models available to write some parts of the code, but what is important is to critically analyze the output that you get from even the code that ChatGPT might write for you, or you can write yourself as well, and to analyze it and to think about there is space for improvements. How can we improve it? What kind of accuracy you achieve and so on, and if you want to improve, how to improve, and if you improve it, you have also, or if you compare different models, which of them is outperforming the others, and you have to justify and to find reasons behind the output that you get. This is what we want and we aim from this course, let's say, rather than focusing on the programming elements itself, because there has been some questions around in the morning asking, I don't have a solid background in programming in Python and so on, so don't worry about that. So it will be more focused on explaining the output and thinking about how we can improve it and so on, and part of the code will be delivered to you, including also the project.
Great. So we're going to start with a lecture. We're going to do the fundamentals, all the different aspects of a basic neural network. I highly recommend you raise your hands during the lecture, interrupt us with questions, okay? And we move from there, all right? So Gerta will go through the fundamentals, and then I'll go to the next set of slides, which is how do you code? This is working, so you can. Okay, yeah, whatever you like.
So in the first part, we'll focus a bit to explain, because we will work on different types of neural networks, starting from tomorrow, convolutional neural networks and so on. But let's understand first what is the basic unit or the core component in a neural network. And after that, the neural network itself becomes 1,000, millions, billions of these nodes that they are connected, and they are becoming very powerful model nowadays, and they are widely used in order to be used in different problems. It can be prediction problems. For example, we want to predict the prices of houses in Flora and so on, or it can be classification if we want to classify records that we have belonging to different classes, binary classes and so on, depending on the task that we want to solve. But let's understand what is the core model behind it. Going back in 1949 and 1950, scientists wanted to imitate the human brain, which I also consider nowadays that this is one of the organs that is not so discovered or well explored, let's say. And they wanted to imitate the human brain and the neurons, the biological neurons, and to create artificial neurons, which is the core component in the neural networks and so on. In terms of, in here you can see an analogy between the biological neurons and the artificial neurons. In terms of the biological ones, so we know that we have dendrites. We think they are like branches, arms, that they get the input, let's say. And after that, there is a processing unit, which is the most important one, the soma cells, and with the nucleus together, where the processing happens in the neuron. And we have the third part, which are the axons, and the axons itself, let's consider them like bridges, let's say, or paths, where the signal output is going to go from one neuron to another in order to connect neurons between them. The same for analogy happens in an artificial neuron. What will happen in an artificial neuron? We see in this image on the right, so we have a simple one, what we call a shallow network, where we have 3 layers in here. It's evident that the first layer is always the input layer, and there is the output layer at the end, and in between we have different hidden layers. In the simplest architecture of the neural networks, we have a hidden layer, and here we have just one hidden layer, and we have these neurons in the layers that they are connected. If you see this architecture of this neural network, this is a simple one, because we have just one hidden layer, a shallow network, let's say, and the neurons, in the first one, in the input layer, we have 3 neurons into it. There is a hidden layer that we have 4, and in the output layer that we have 3. If we think about the input layer, these neurons, they do not do any processing at all. So in the first layer, the input layer, this type of neurons, they are used in order to get the input. What is the input? The input is the data itself that you have. Let's consider that you have an Excel file, a CSV file, with millions, thousands of records into it, and you have some features, variables, columns with data in an Excel file. Let's say this is what it will be in the input layer. And the input layer, you are not going to configure in terms of defining how many neurons you are going to have in the input layer. So in the input layer, it depends on the features that you have. If in the data set about house prices of houses in Flora, you have, for example, 3 features. It can be location, it can be number of beds, and it can be, I don't know now, it can be number of bathrooms. So this will be the 3 neurons belonging to the input layer, depending on the data that you have. In this one, we have added a hidden layer. You see that all the networks from input layer to hidden layer, they are fully connected, and this is one of the types that we have when we talk about architecture of the neural networks, when they are fully connected. In terms of the last one is the output layer. So every neural network that you are going to deploy or to create, it will have an input layer, it will have an output layer, and there will be some hidden layers in between. Saying that, why we call it deep learning? It's deep in terms of having many layers in between. As more layers we have, it will be possible to model complex relationship with real data sets. Less hidden layers we have, less we can model, or not in a better way can we model this complex non-linearity that it exists in real data sets. So in terms of, you see here machine learning, where machine learning stands. These are multidisciplinary now. Myself, I've been teaching different modules. Let's say in all of these disciplines. So I've been teaching data mining in the University of Iran. I've been teaching databases, and I'm still teaching now databases about how to store this data and how to go on with pattern recognition and so on. It is statistics, it is AI, and machine learning stands in the overlapping between all these different fields. This is where machine learning. But there is a difference if we compare what statistical modeling means and also machine learning. The statistical modeling itself, it is based on interpretation and causality. When it comes to machine learning, we are focused on precision and prediction. So we want to predict the price of the houses, and we want to do classification depending on the problem. We want to classify and so on, and this is our focus. When it comes to the mechanism, think about most of you has experience working in statistics with different models, such as simple linear regression, it can be multiple linear regression, and so on. You talk about parameters. Let's estimate the parameters in these models. Now, in the lecture today, but during all this week, we'll not talk about parameters, but we'll mention weights, and I'll explain in the coming slides what weight means and why the weights are really important as an important mechanism in order to train the model or to do the learning process of a neural network and so on. And in terms of the goal, the statistical model that we use, the goal is about dependence analysis, and when it comes to machine learning, it's about generalization. When we work with machine learning models and also deep learning models and so on, so we have a full data set, and we usually split it into two different subsets. There is a training one and there is a testing one. In the training one, usually we recommend to have 70% of the record belonging to the class of training. We want the model to train itself, and after that we keep a sub-part of our records that we have. It can be, when I say it can be records, it can be images, depending on it can be articles for the project as well that you use in order to train, to test the model, how good the model is, because the testing is really important. Sometimes students report the statistics or the evaluation metrics related to the training. It's not that we are interested when we want to see how good the model is. It's not about the training itself. We want to see about the testing. The testing is a process that you feed in a neural network, or it can be any machine learning model such as support vector machine and so on. You feed in some new data that the model has not seen during the training process. And these are the evaluation metrics that you have to report, because there is also something that this is not very clear with students. So they run these kind of models and they come up with presenting the evaluation metrics that they receive during the testing, and not during the training, and not during the testing as well. In terms of now, if you understand here with these slides how this artificial neuron works, it will be easier for you to understand all the different types of neural networks that we'll go through during this week. So there is artificial neural networking here, and now the dendrites is the input, the data itself, x1, x2, x3, up to xn. What that means? The data that you have in a data set, in a text file. You have the, let me go back to the example of the prices of houses. So what you can have the number of bedrooms, the number of bathrooms, the location of the apartments or the properties, and so on. So all these are the data. So these are the input, x1 up to xn, depending on how many features you have in your data set. Now, what happens? There is now a processing unit that we call, similar to the cell body process, that happens. It's going to do some transformation, some processing in there. This is important to understand what happens in there. So you see now that there is a summation or weights. What does that mean? Now we need some weights in order to show which of these features that we have, or if this input is more important than the other, and how it starts with the neural networks. First of all, these are randomly assigned. There will be some numeric values that they are assigned to all these weights. All the connections, you see now, x1 up to xn that we have, they are going to have their corresponding weights, w1, w2, w3, up to wn. These, when we start to train our neural networks, are going to be assigned randomly, with random values, okay? And now what happens in the processing unit? There will be, we now are going to multiply, so all this input is going to be multiplied with the corresponding weight, and we have to sum them. Do you understand what I'm saying? So now what I have to do? We have to multiply x1 multiplied by w1, which is the weight, plus x2 multiplied by w2, plus x3 multiplied by w3, and so on, and to calculate the sum, and it will be a numeric value that you get out of this. Okay? So now what we want? Now we want a process to happen, or something to happen in that one, in order to go and get the output, the outcome that I want to get. It depends on the task that I want, that y in here, that is the output. If it's the house, the price, it will be a numerical value for the house. It's a prediction in this one example. If it is a classification problem, I will need to know now. This, for example, I have some emails and I want to classify this based on the content that I have the email, if they are spam or not spam. So this is a classification problem, a simple version of a binary classification, just to classify the records into two classes. And I want now the y to be ones or zero. Once, it will say that this record or this email belongs to the class 1, spam. 0, the record belongs to class 0, which means no spam. So this is what I'm expecting from the y. But how this happens now? So this is what happens. You have the inputs, your data, x1, x2 up to xn, all the records that you have in a text file. I'm taking a simple example. You have the corresponding weights. For the first one, randomly assigned values. It can be 0.4, 0.2, 0.3, things like numeric values. The first one is 3 bedrooms, 3 multiplied by 0.2, plus 2 multiplied by 0.6, plus 0.5 multiplied by 0.7. And you sum that one. And you have a numeric value there. So this is the first one. So you see there are 3 steps in here. What happens? The first one is a linear input function. You sum the weighted inputs, and you have the net sum. Now, what happens? That net sum that we have is not enough. It's like capturing linear input function. And we want to happen to do a transformation. We want to transform it. And how we can transform it? This happens during the activation function. We call it activation function. There are different activation functions, many of them, but in the next slide I'll introduce to you 3 of them that are widely used, let's say, starting from the sigmoid and so, but it's important to understand what this activation function does. They are going to transform now all these numeric values that you get, the net value that you get, but why we want to transform it? Because now we want to introduce the non-linearity. This is really important because neural networks are becoming very popular, not only of working with big data sets and big data and so on, but because they can predict and they can model the non-linearity. And when it comes to real data and the real domains that we work, usually we don't have linear relationship between features, variables, problems that we want to explore and so on. In real settings, we have the non-linearity, and this is where we want to introduce the non-linearity, and this is what the second process of activation function does. And I'll show how it is done, and based on this activation function, what do we want to do? We want to go to the output, which it will be a result now, that this specific neuron is going to calculate, to transform using the activation function, is getting a value now from the activation function, and now this output y is going to be an input to the next neuron that this neuron is connected. So this is how it works. Saying that, keep in mind that a single one doesn't contain any intelligence at all. So if I have only a single one, the intelligence and the power of all these neural networks comes when all these networks are connected, so where I have all these layers that we have been talking about, and where all this is connected, and we go deep and deep with having more layers in between. So now let's have a look to the process in here. There is a threshold and bias that I want to mention. What happened usually? So after we calculate and we get this value, so you sum, and the value, for example, it can be 2, it can be 1.7, and so on. Now I want to, this is like a classification one, so I want the output to be 1 or 0. So now what I have to do, I have to compare that output with a threshold. We call it this threshold with the symbolic of theta from Greek symbols, and now we compare it. This is the threshold theta. This is a constant that we have. So if that sum that I calculated with multiplying all the weights with the input with the corresponding weights is greater than that theta that I have, I'm going to output 1. So that neuron is going to light. Otherwise, if it's less, I'm going to classify, or the output it will be 0 belonging to the other class. Did you get it? So now, what happens? Rather than working with the theta itself, you see that in this slide, we are introducing the bias one. So the bias is not something new, let's say, it's the theta itself, but what happens? Rather than having the theta on, on the right side of the equation, now what mathematically, all of you can understand it, is that if now I say that B for bias is equal to minus theta, now I can include that component on the left side of the equation. But this is not the purpose that why I'm moving from theta to bias in the concept, because saying that theta and bias, they are the same thing, let's say, mathematically. But why we are doing it is not only to represent it in a better way, to have everything on the left side and to compare with 0, because is that greater than 0 or less than 0 now? This is the comparison that we are doing, the threshold. So it's not comparing with theta, but if I have included the bias in that, so now the comparison, it will become if the sum, the net sum, plus the bias is greater than 0, the output it will be 1. Otherwise, it's going to be 0. So the main reason in here is not about having that one on that side, but it is because now the process of learning, the network itself, is going to adjust the weights, to change. I told you at the beginning that the weights are randomly assigned. So if a record now is wrongly classified, the network itself is going to learn that, oh, this is wrongly classified, so I have to improve. What I have to improve? The network itself is going now to change. It is going to change the W, the weight itself, but it can change also the bias itself. So these are some parameters that we use. Now, here, but what happens? How they are changing? So you have the weights 0.2, 0.3, 0.4 with the example that I'm saying. Now, should we change this weight, or should we keep them as they are? So this is the question in front of us. So if we want to change if the model is not performing good, so we don't get the desired output. If we get the desired output, don't need to change the weight. What does that mean? What is the mechanism behind changing the weights? This is really important to understand because this is the process of learning. The network now is starting to learn. So how to change it? In order to change, do we need to change or not? What we have to compare in order to change? What do you think? What is important to compare? No tolerance. What?
The result and the correct answer.
That's correct. So what we have to compare? We have to compare the prediction, what my models predict, and what I have in my real data. Because I forgot to mention at the beginning that when we talk about neural networks, in machine learning we have supervised and unsupervised. These are supervised problems. What does that mean? You know that the first record, for example, belongs to class 1 or class 0 and so on. And now what you want to do? You want to compare. So based on what we did with the theta and comparing with the bias or the threshold, now you calculate, the model is predicting. The value that the model is predicting is y. Okay? So the model says that this belongs to class 1. Now I say the neural network, check the real data. The real data is the target one, is W is that hat. Now, if they are identically, so no need to change, because why? It's class 1, the model is classifying to class 1. Why should I change the weights? No need to change at all the weights, I should keep the same weights that I have. Okay? And that is here, even mathematically, if you see, the delta W is how much I should change the corresponding weight now. And in order to change a corresponding weight, the formula is there is an alpha, which is a learning rate that we use. We multiply with the value itself that you have in your data, the data set, the Excel files that you have in your mind, and you multiply with the difference. Now, if there is a difference between the actual outcome and the actual data that you have and the outcome of the model. Now, you see mathematically that if y is equal to y hat, so the prediction is equal to what you have as actual, so it will be 0, there will not be changes in that specific weight. There is no need to change that one. Okay? So if there is a need to change, you are going to change. You see now that I mentioned alpha in here, and that alpha is the learning rate. Usually it's a constant, a small constant that we play with it, let's say, but usually you see here that we have also put it as 0.1, which is a controlling speed. It's important to consider this kind of values that you apply to alpha or to the learning rate, because if you put 2, 3, 4, what happens in these cases? You are going to do dramatic changes to the weights and you will not converge. So converge means that you will end up in a situation that a perfect one, it will be that you have 100% accuracy. But in practice, with real data set, with the data set that you are having with the project with thousands of articles for Albania and so on, you never can reach that 100%. And this is a flag, let's say, even when students come with me, or even companies that I advise, comes with this kind of output, I always say, oh, there's something if I see very high results, up to 100, 90% with real data I'm talking about. Not small data sets, synthetical ones, because they can easily converge. Why they? Because in practice you cannot have a perfect models that can achieve a 100%. But why it happens? Because they are not manipulating the figures. They can end up with situations that they achieve this high accuracy and so on. This happens due to what we call in machine learning about overfitting. So the model is now learning from the training data set and so on very well, but it cannot be generalized during the testing and so on. So this is the problem of overfitting, and we need to figure out if we have overfitting, to discover it, and if we have overfitting, we have to think about how we can mitigate the overfitting and have some strategies in place and so on. So in here, the alpha, as I mentioned, we need to put a small value, 0.1, but you can also play with different alpha and so on, because this kind of work that we do with machine learning, deep learning and so on, we never consider them only being as a science. It's a science and the art, and when I say the art, it's because we play with all these parameters, we rerun till we achieve a desired output, and that is important to know. So if the alpha is very, very small, 0.001, so it will still, you will have so many situations or taking place that you are going to change that weight and so on. So that's why it's an important element, that learning of rate, because this controls the speed of changing of the weights, but also how many epochs you are going to run your neural network and so on. Let's have a look in here. This is the first one, the epoch one. Can you tell me what are these alpha in here? This weight, sorry, 0.6 and 0.5. It's there, it's random, yeah. So, as this is an epoch, first epoch. Do you know what an epoch is? No, it's not generation of the eye. Do you know what an epoch means? Epoch, yeah?
Period of time.
Okay, so let's suppose that I go back to the example of prices, house prices. So I have 1,000 records in my data set. I collected 1,000 records for 1,000 properties in Flora, and this is what I have in my Excel file that I'm going to use and to train my model and my neural network. So once all these 1,000 are feeding in my neural network, so I finish all of them. So this is one epoch. I'm done with one epoch. All the records has been processed, has been going through the model.
One iteration.
And yeah,
No.
of the whole data set, not iteration.
Not
It's not
iteration.
It's not iteration because you can have batches as well.
Yeah,
but I'm not-
so,
Yeah,
sorry.
you go.
So there is a difference. I mean, there are three main terms. We're going to see soon. It's called the iteration, it's called the epoch, and it's called the batch. Okay, so what Gerta is mentioning, the epoch, is actually how many times the model sees the data.
Full.
Full. So think about yourself as well. When we are working with data, or when you are trying to learn something, right? If you read it once, would you be able to memorize it? No. Second time, better. Third time, better. So every time you read it, that means that you are receiving all the information from the book. That is exactly here what is happening. The model, which is your brain, sees that whatever is written down, the data, multiple times. And the network, the neural networks actually need to do this simply because the training of the weights is not as straightforward as we imagine. We are talking about millions of parameters, and in order to actually do a good job, in order to estimate all of those W's, it needs to see the data many times. Okay?
Yeah, and saying that, think about, for example, we feed in the first record in the data in the neural network. We don't change the weights; they are correct. We feed the second. We don't change the weights; they are correct. We feed in the third one. Oh, now they are not properly classifying, so we have to change and update our weights using the learning rate and so on. We change the weights. What happens? It can be a situation now that the first record and the second record, that they were correctly classified with the new weights now that we change in the third one, so they are not correctly classified anymore. And that's the need that when you fix all of these things, when you go to the next epoch and so on. Okay? So now if we go back to this example in here, in the first one, what we have? We have a classification problem. So we have two classes. The first one are some dots or some objects in green, and the other one are what we have in orange, let's say. And we want now to have a decision line, which is a straight line, let's say, in order to classify and to classify the records that we have, or the data point that we have in this example here. In the first epoch now, we have some random weights, 0.6 and 0.2. So we have just x1 and x2, because we have only two weights in here. And now the error is high. Why is high? Because we have some data points that they are wrongly classified, belonging to the wrong class and so on. What do we have to do now? We have to move to other epochs. So we continue to train, and the model continue to learn, let's say, and with the data itself that we have. So there should be an epoch 2 that we have not presented here. We go to the epoch 3, so third round now, where the model is going to process again, to see again all the data that you have. Okay? In the epoch 3, we see that the weight has changed because there is that learning process, so using the alpha that we mentioned and so on. So they have changed from 0.6 and 0.2 to 0.44 and 0.16, so they have been adjusted now. You see that even the decision line has been changed now, okay, the slope, and also the error has decreased, but we are still not in a desired outcome because we still have some records that they are wrongly classified. So we need to move to the next epoch and so on. If we go to the epoch 6, and this is a simplified version, these are not real world data set, that's why on epoch 6 we achieve a situation with the error is 0, but in practice it never happened, let's say. And the weights in here are 0.2 and 0.1, which means that it's stable, and we say that it has converged now, it has learned, and we are satisfied with the results that we have obtained from our model. Yes.
And I want to add something again, but you go first.
So how many epochs would you consider that enough, or probably enough, for the model to learn?
Who wants to answer? Me or me?
Both of you, or
I
you
will continue that you go, and I will continue with
Okay,
this.
so great question. So I'll repeat the question. The question is, how many epochs do we need? Or do we know how many? No, we do not know. Okay, so the more we learn, the more epochs we add, is it going to improve? The answer is yes, it will improve. But we're going to end up with a danger. It's the danger of learning too much information about the data, so the model eventually won't be able to generalize. And what do I mean generalize? When I give something new, the model that has never seen in the training phase, it won't classify that correct. Okay? It's the same thing again as we are processing information. The more we read, the more we memorize, the more difficult for us is to actually generalize to something new. Okay? So math problem, someone tells me, okay, memorize the solution. I memorize it, I'll be able to actually write it again and again down correctly, but if someone changes slightly something on the exercise, I'm gonna fail. Okay? Same thing happens here. So at the end of the day, epochs is the, something that you have to tune, okay? But there are some strategies, okay, to select also. I want to say something else about the straight lines here. So you see these three evolutions, right, of the model. Okay. Question number one for you to think. Why two parameters? Yeah.
Because there are only two colors, green and orange.
Okay. I'll save your answer, but I want to hear more answers. Yes.
Because of the line, the kind of line that we are choosing to separate. It is a line, it is a straight line, so a straight line is just two parameters.
Other answers? The closest answer is this, I think that's the correct one. So when you have a straight line, you need only two parameters to characterize the straight line. Go back to middle school. A straight line needs the slope and the intercept, right? Two things. These are the two weights here. What you see here going from epoch 1 to 3 to 6 is that the line is actually changing. So what we are doing is actually we are changing the slope, and that's why you see the line is rotating. That is actually the goal of most algorithms, to find the right position of the line that will separate the two classes, the green and the orange. Okay? Now, the more deep you make the model, the more parameters, but then there is not a straight line. What is happening, it becomes a plane, and in the n-dimensional space, millions of parameters, it becomes a million-dimensional hyperplane. Okay? Now, question for you, second, sorry. What is the role of the activation function? Do we have any activation function on what you see? Yeah? Other question? Other answers? I'll say it.
It would be like a decision line because you said before that it's like a transform from the net vector to one nonlinear. You should decide.
What you see here, this is a straight line. Remember what Gerta mentioned about linearity and non-linearity. Okay? When we are talking about a straight line, we didn't add any non-linearity there. Otherwise, you would see the straight line to become a curve. Okay? So here, it's a straight line. It's the line that we are actually using in middle school, which is like y equal a times x plus b. Okay? And that's what you see here. There is no non-linearity. Now, if you want to add a non-linearity function, that is when you are actually taking the function f and you add and you apply it on the ax plus b. And this curve now becomes, and this straight line now becomes a curve. Make sense? Great.
So there is
Yeah.
no activation function here?
There is no activation function here, and we do not need an activation function there. By the way, now you need an activation function, and I'll tell you why.
So, you see on the left side in here, so we want to separate the data into two different classes, and this is possible to be done using a straight line, as we have been talking, so no need to have any activation function at all. So it's just a straight line based on two weights, and we have that line in here. A single perceptron works perfectly here for linearity. But I told you that in practice, the problems that we have to deal with, they are not linear problems. So we have now to deal with the aspects of non-linear. And you see there is a restored problem that we have. So you have different classes in here. Even if I ask you to spend hours and days, you cannot split the data points in here using a linear line or using a straight line in here. No one can do it. It's not possible at all. But how to do it? How can we do it? Because we have to deal now with all these word problems that they are, most of the times they are not linear and so on. In order to do it now, the solutions comes with what we call multi-layer perceptron. What does it mean? I'm talking about layers now. So rather than having a single neuron, let's say, so I need layers now in order to deal with that. And now you see in the first one, so it comes with dealing with the complexity that we have, but with going to deep networks because we want to have different layers in order to model the complexity. What happens? Let's suppose that in the first one we are having just the first hidden layer, what we have been looking till now, and in the first one we are using that first hidden layer, so we are going to split what we have in half spaces. So this is what we do with the straight line, split into half spaces. Now, if we add a second hidden layer, that will be after the first hidden layer now, which you see now, the second hidden layer will allow us to go from the half spaces that we have to convex regions. How this happens? Because now the input that we get from the first hidden layer, these half spaces that we have, are the input that will be processed and will be moved to the second layer, second hidden layer, in order to end up with that convex region. So this is what happens. So now, adding more hidden layers, it will make possible to tackle the problem that we have with non-linearity in our data set, in our problems, and so on. So that's why when we are going to configure our neural networks, adding more hidden layers, so we make these networks powerful in order to handle this non-linearity that we have in our data and so on. And when we achieve and we go to the last layer, which is the output layer, so now in this one, what we have? We have an input layer, we have two hidden layers, the first one that will end up with half spaces, and the second hidden layer that is going to end up with convex regions. And when it comes to the output layer, that now I want to separate my data points into different regions and so on, so I have here arbitrary shapes. Okay? So this happens. But what is here? The hidden layers can solve this non-linear problem that we mentioned, but it's also important to think about the feature extraction. When we work with machine learning models, let's say, so everyone spends some time about feature extraction. You can have data sets where we can have a huge number of features, and we want to identify which of the features are more important, more relevant, and so on, and what we call feature engineering, and to extract the most important features and so on. In here, it happens also the process of feature extraction, because the hidden layers are going to define the hyperplanes that we have, that intersect with specific data regions and so on, and saying that if we move now from a single neuron to what we call a multi-layer perceptron, we now are tackling the problem of non-linearity that we have in our data. But how this happens, and this is where Zoe was talking about the activation function in order to understand what happens in the activation function. In here we have shown only the three widely used, let's say, activation function. There are others that you can explore yourself. The first one is the sigmoid one, which has been used in the past, and what is activation function? I told you activation function, they transform. So there will be a transformation. Now what happens now? It's going to smooth the transition between 0 and 1. So you see now the function becomes it deals with the nonlinearity because the shape now of the function is like an S, you see. And what I'm going to have after transforming the net sum using this sigmoid activation function, the output that I'm going to have, it will be a value between 0 and 1. And this has been one of the most widely used in the past as the activation function. The other one in the middle, which is the hyperbolic tangent, is another one which has a similar shape like S as the sigmoid one. And but the output that we get during this transformation, it will be something between -1 and 1, and it has an advantage compared to the first one, which is the sigmoid, due to the fact of stronger gradients than sigmoid. But you will see that during the exercises that you work, we are going to use the widely used activation function, which is the ReLU, and it stands for rectified linear unit that we use, and it's a simple one, let's say, but it's like the modern standard for deep learning nowadays that we use in our hidden layers, because we don't have activation function in the input layer, we have the activation function in the hidden layers. And now what this function does, if you see the function itself, it will be equal to the max of 0 and x. So what happens? For any value that you have, if the value itself, the net sum, is a negative value, the function transforms or gives a 0. If otherwise, for positive values, you keep the value that you have. So this is what the function does. You can also have a look to how the function looks like here. So negative values are transformed to 0. Positive values will keep the value itself. So this is what the ReLU activation function does. And this is also solves the vanishes gradient problem, which is a problem when we talk about feed forward and backpropagation in the next slides. Now, we talked about how we train a neural network. So you have the data sets, you have input neurons, hidden neurons, all the data pass through these layers, let's say, and in the neurons, transformation happens in the hidden layer, activation functions that we have been talking. It doesn't matter if it's sigmoid, ReLU, and so on. And we have the output, the prediction. Okay? So if the output now here, we do, once we get the output, or the network calculate the output, now we have to calculate what we call the error. So we have to predict, we have to calculate the error or the loss. So what we do? We compare what the model is predicting, what we have actual. If we see that there is an error, let's say, they do not match. Now, there is a need what? Let's go back. That's why we call the other process now, backpropagation, and we are going to play a video later in order to see how it works and so on. And there is that backpropagation process that happens, that we go back, and what happens in that one? Because this is a cycle, what the backpropagation is doing. If we have an error, what I have been talking, what we have to do? That's correct, we have to update the weights. Okay, so using the learning rate and the formulas, we have to update the weight, and after the weight are updated, what next? We are in a cycle. So once the weights are updated now during the process of backpropagation, so now we continue again with a feed forward. Okay, that is a cycle in order to understand. Yeah.
How much does it happen for the error to be 0?
To be 0 the error. In practice, never.
Okay.
In practice.
Is there any threshold under which the weights are changed or not? I mean, threshold for delta W.
No, there is
Under
no
which, or only if it is 0, we have no changes.
They will not change if the actual outcome is equal to the output that you get. They will not be changed at all.
But if it is
They will be changed, and it depends on the alpha, the learning rate, the change itself.
How many times is this cycle done? How many times?
What do you think? How many times it happens?
As the weights.
I go back.
So basically, when do we know that we're done with trying to predict errors?
Maybe when
She wants to answer it.
Yeah.
Can I say something
Yes.
about that? Because I've worked a little bit with the residual networks and units. So the model stops kind of doing the cycle when it predicts the same. So when the input
Exactly the
weight
same or close?
the same, when it doesn't learn anymore. So when the epsilon or y is the same with the y with the tone,
Cat.
will be the will be the same. It will stop learning. Is it closer?
Kind of. There is something.
Depending from the size of the error, I think, we will continue to train the network until the size of the errors is achieved.
Okay.
Yes, this is the condition that the training stops, or how many epochs do we want to do?
So all of those answers are valid. Okay. However, there is something deeper than what we are trying to achieve right now. So there is something that we haven't actually explained pretty deep. It's called the backpropagation and the gradient descent. So at the end of the day, what are we trying to do? It's parameters, W1 through W1 million. Okay? So those parameters actually, along with the cost function that we are trying to minimize, which is the error, generate a surface. This is the one. Do you see it? Okay? So that's the function with the parameters. If you want to mathematically draw it, that's the one. Okay? Now, if you see here, there is a position at this surface that actually minimizes the error. Okay? When we say minimizes the error, we are looking at the lowest place in that surface. Okay? It's here. Yeah? So, the algorithm will stop when the weights or the set of the weights point to this direction, points to this position here, to the lowest. This is when the algorithm will stop. Okay? And then this is the place also where the error will become 0 almost. Right? Now, what's the challenge here? This is an iterative process. Okay, so what it means, and Ogerta will go through, but at this surface here, we have to randomly start from somewhere. Remember that the weights that we initially had, they were random weights. That means that these weights can be located anywhere here. Okay, and now it's a matter of luck and good training to actually go to that direction, to this minimum block. Okay? Is this something sophisticated? No, it's not. Actually, we've done this in high school, but not with those type of surfaces. We have done it with simple functions. Do you remember when we were saying, you have a function f of x equal to x squared, like this, the parabola, and then someone was telling us, can you find the minimum value of that function? Yes?
Yes.
All right, then what did we do? We said, okay, I'm going to take the first derivative, 2 times x, set it equal to 0, and x is equal to 0. That means that in that shape, that point gives you the lowest value for the function f. That's what we are trying to do here, but instead of just x, we have w1, w2, w3, w1 million. Okay? Now, we cannot solve it by hand, and that's why we are going to gradient descent. Gradient descent is an iterative process where, with a couple of steps, it will take us to the minimum value, to the set of weights that minimize this value. Good?
So I'm not going to focus and explain in detail this one because this is what we covered. So the first one is the shallow network that we'll be looking today, where we have just the input layer, the output layer, and one hidden layer in between. And this is the basic, what we call multi-layer perceptron, one direction, feed forward. The other one is the recurrent networks. We'll look at it on day 3, where you see now that The network has been changed a bit. If you have a look, there is a cycle in it, you see now, and that is the memory, that are connections from cycles, and this is, you see, when I mention memory, it means that these are suitable to be used when we work with time series data, but also in NLP, we use, myself, I've been using LSTM, which will have a dedicated session for long short-term memory type of recurrent networks, and the other one is the deep convolutional neural network. When you see that the word deep means you see it, there are so many layers in between, hidden layers, and this type of neural networks that we'll introduce tomorrow, they are used for image recognition or image processing, let's say what we call it under computer vision. This is something important to mention because as they are very popular now, these neural networks, everyone think about, okay, you have a data set, you want to make some prediction models and so on, and let's deploy a neural network into it, let's make it as complex as I can, let's include so many hidden layers and so on. But that's not how it works in practice. So in order to use a neural network, you need some justifications why you have to use it. And you see here that we have listed some criteria. The first one is heavily dependent on the nature of the data that you have. It makes sense to use neural networks, convolutional neural networks, if you are processing images, if you have sensor data, if you have articles, textual data, and so on. Maybe there are some situations that there is no need to go and use neural networks. You can build a simple machine learning algorithm in order to do that kind of classification of prediction. I had an example where a student in his master had a data set about road data in the UK, and he wanted to predict some accident. It was a very simple data set with only 3-4 features into it. Even the total number of records was not enough in order to go on and deploy a neural network and so on. So it's really important that the input of the data is high dimensional, such as images or sensor data and so on. But something that makes them powerful is also about noisy. When we work with real data, they are noisy, or we call it dirty data, in terms that you have quality issue in the data, inconsistency in the data that you have to handle and so on, but also we have missing data. What does that mean? So a lot of records might be missing, or it can be different values for different features that they are missing and so on. In statistics, how we deal with that? Sometimes we go through different imputation techniques, so we can impute it using different imputation techniques and so on. When it comes to machine learning, we have to predict most probably the missing one, because some of the algorithms that we have in machine learning, they are not, they cannot tolerate this missing data and they do not work at all. But when it comes to the to neural networks, so they can fit quite well the data that they are noisy, and they can contain also incomplete because they are resistant to errors. If we have nonlinearity dynamics that we want to predict and so on, so they are a good fit to go on with neural networks. But also, it depends on the domain that you work on. It depends also if you want to know what happens with your data, and if you want to audit what happens during all the processing and so on. When it comes to the neural networks themselves, so they are considered like black box. So it's like you don't see the output, what you can get from one hidden layer to another, how the data are transformed and so on. What you get, you have the input, you run your model, and you get the output at the end. So saying that, you don't see what happens in between all these layers, and that's why you consider them as a black box, and you can deploy and use these neural networks in the situations where the interoperability is not a priority, depending on the company or the sector that you are working and so on. In terms of the trade-offs, because we know that there are so many advantages to them, they are becoming very powerful nowadays and so on, but there are also some cons with it. And the first one that everyone is dealing with is the fact of they are expensive in terms of the computational power that you need to run them. Think about millions of records with millions of features that you have to train these models and so on. When we mention that weights, if you think about billions of neurons, there will be billions of weights that they have to be updated, number of epochs that I was explaining, all these data that they have to be fed in again and so on. So think about this kind of complexity, and that's why it becomes a cons. There is a risk of overfitting that we mentioned, and overfitting means that you cannot generalize your findings because the model is learning about the data itself and so on. And what we talked about, interoperability, and difficult to explain why something might happen and so on. Yeah.
So, for the data, because I've been working with images, and how important is the processing of the data before the giving to the model? And what will be the disadvantages that the model will have if we don't process it well, or if we don't do it at all?
So what kind of images do you process? So,
MRIs?
gray, color images? Like
Yes.
Okay, and what kind of preprocessing do you try?
So rotating, slice extractions, how important will be, or let's say what kind of disadvantages will I get if I don't do the preprocessing of the data?
I think that in terms of, we have a saying that the AI models that we have, it doesn't matter machine learning, deep learning, and so on, they are as good as the data are. So it's not that you can, and saying that you have to spend time on data pre-processing, including images or other data types that you might have and so on. So it's not about, you can configure a very good neural network, so many hidden layers and so on. If the data that you are training your model are not enough, are not good enough, let's say, so this is like what we say in information system, garbage in, garbage out, let's say. And this is important. We have to spend a lot of tasks of pre-processing the images in a proper way in order to use these neural networks. I think that there is a slide about some examples in here. Yeah, this is like a case study that I'm moving fast through it. So let's say that we have a problem, and this is using fraud detection. So we want to build a neural network, but let's first of all understand the nature of the data that we have. So we have around 10 million rows of data, and we have around each of these records, let's say, contains 150 features, and we are going to run it in a Hadoop cluster. Hadoop is a framework that we use in big data, and we have 800 nodes into it. Nodes are servers, machines, let's say, to think about. So what happens now? After we run the model and so on, let's have a look to the results that we can achieve. We see that based on, here is the number of neurons, but I think it should be the numbers of layers, let's say, or the complexity of the network itself, not of the neurons, but of the layers. So if we have two layers, which means that we end up with a shallow network in here, the accuracy that we achieve, it will be around 0.76. This example here is to show to you that as the model becomes more complex, so we move from 2 layers to 4 layers now, so the accuracy is going to be increased, and we achieve an accuracy of 0.82 in here. And if we move to complexity of 6 layers and 8 layers, we see that still there will be an increase in the accuracy of your model. So starting from with two layers where we have 0.76, we can achieve an accuracy of 0.83 with 8 layers. But someone might say that, okay, maybe this is not a big improvements in terms of the accuracy, but we are talking about fraud detection in financial system and so on, and that means a lot for the domain experts, let's say, moving from 0.76 to 0.83. Okay, it's not just a small step, let's say, in terms of improving the accuracy from 0.76 to 0.83, and these improvements comes from the complexity of the neural network, because the improvements must come from different reasons. It can be you go back and you do a better pre-processing of your data. It can be due to changing and improving, making more complex neural networks and so on. It can be of changing any of these hyperparameters that you have in the neural network and so on. So that's why I told at the beginning that this is art and science at the same time.
Can I make a question?
Yes.
So does it mean adding more layers, the system becomes more intelligent, let's say?
Who wants to answer this?
Yeah.
That's
You
a very
answer first
open-
and we will, yeah.
You don't have
It
data.
does get more accurate,
The
but it
number
also
of
gets
layers continues to improve the accuracy, not every, I think, because every hidden layers, systems will finds new features. hidden relation features, other features
Okay.
in every given layer.
So the answer is
The architecture is
yeah. The architecture. So let me go directly to your question. I think all of those are valid points. The more you add doesn't imply that the more intelligent the system will become. Okay. So it doesn't mean the more the better. All right. So, however, the neurons and the layers are actually, at the end of the day, user parameters, meaning that you have to set them up, meaning that you have to do something called hyperparameter tuning. Okay, and based on a particular metric that you are interested in, for example, accuracy, you should set up a framework. That actually is a perfect trend, and if you see that the more you are adding, nothing will happen in terms of the accuracy. Okay? And actually something dangerous will happen. Overfitting. What is overfitting? Remember, we won't be able to generalize to unseen data. Data that the training model never has seen. Good?
Yeah, logically it makes sense that when you have just a hidden layer and you move to 2 hidden layers, 3 hidden layers, 4 hidden layers, at the point of time you continue to improve the metrics, the accuracy itself, let's say. But at the point of time when the number of layers, the network has become so complex and so on, so you are not improving the accuracy or even a small improvement in the accuracy, there is the risk of ending up with overfitting, which the model cannot be generalized, and we want to generalize the model. It's not just to have a model that can predict the records that we have, because we have them, we know to which class they belong. We want to have in place a model that can predict the record that has not seen. That is the risk.
So if adding more and more layers doesn't help, what are some solutions to improve performance? Like in this case, fraudulent transactions may be very small and simple size versus the normal transaction. But how to improve the performance of fund both small and very dynamic judging fraudulent transactions?
So that what you are actually asking, if I understand correct me if I'm wrong, is actually a trade-off between how many training data you have versus what targeted accuracy would be. So again, doesn't mean that the more data, the more training data you have, the more layers you have to add. You mentioned a word called dynamic, meaning
It's not that.
right, meaning that over time the 10 million rows will become 15 million rows. Okay, so that is actually, that has many solutions. A first solution, the naive solution would be that, okay, once I have new data, I'm going to retrain the whole model from scratch, meaning that I have to actually reorganize or add more layers or remove layers, in other words, do again a hyperparameter tuning, okay, in order to achieve this accuracy or even higher accuracy, because I received more data. I'll let you think what the disadvantage with this is.
It's more complex and more complex and more complex, bigger and bigger, it takes more time to train.
Yes, and then over time, the more data we receive as an organization, that doesn't mean that we have to rerun the model every day, right? It's going to be computationally expensive. Plus, we may need the energy of whole Albania in order to retrain every day a huge model like with millions of parameters. So there is something called online training. That's a different segment of this. Okay, so I'll mention the name, find it out what it means, online training. Okay, and that's for everybody. Yeah.
I mentioned something similar, like earlier, maybe some threshold for accuracy will help. So at first when we reach some accuracy, and then we can stop adding layers. But is there some acceptable accuracy for
That is actually,
as a
that's
stopping
a good
criteria?
point. So this has to do with the organization you are in. So first of all, remember that there is a trade-off between accuracy and interpretability. So the more complex you make the model, the more difficult it becomes for the human to understand the final decision. So, and we don't even know with millions of parameters what the internal activation, how they are updating, and so on. So it's a complete disaster if we add more and more and more. Okay, but the organization you are in should actually make a hard decision before you even start training, whether you want accuracy to be highlighted or interpretability to be highlighted. Okay? Both at the same time is very difficult. So you have to actually sacrifice one of the two. Okay? And at the end of the day, that is actually going back to what Ogerta mentioned before. Do we really always need to use deep neural networks? I make a joke, like you are in this room and there is a mosquito, right? Would you gonna carry a bazooka to kill it? No, right? So this is what deep neural networks are doing. They're very powerful, they're doing a lot of tasks, but for little things, they are not ideal. Whether we like it or not, this is the height, but they are not ideal. We may want to go with a very simple model, like logistic regression, which, by the way, is like a neural network. It's adding an activation function at the end of the day that gives you a probability value, end of story, right? That's all I wanted to say, but we can continue. These are great points. This is, by the way, day number 5. When we are going to touch responsibility in AI, and not only mentioning the interpretability and accuracy, but also mentioning other issues like energy, okay, carbon footprint, whether or not it is worth to retrain a model from scratch, right?
But I would like to mention that these are also very dependent on the domain that you work and on the data itself that you have. Myself working with some companies in construction that have been applied generative AI, let's say, and that's something that we look on on day 4, but and RAG systems and the accuracy we could never achieve 0.9, for example, in the construction domain due to the complexity of the data that we have, to the complex problems and so on. But saying that, also the domain experts are really important in this kind of work. Will they interpret and will they also justify if the accuracy that we achieve is enough or not, and so on. It's not only from the point of ourselves. Yeah, the problem itself, the domain, the data, the nature of the data. Yes. There is not a figure, let's say, that I say if it's not 0. Or 90% is not good, it is good at all, let's say. And yeah, that's about to say. I think that the last slides I'm not going to read, but this is what we covered. So we talked about the inspiration of neural networks. We saw it as a single unit and how important it is to have it, to think about having them connected, let's say, and this is where they becomes like intelligent systems rather than sitting alone as the neurons. And yeah, we talked about the MLP and the backpropagation that we are going to run a video, but I don't think that we have time. We went too deep, let's say, the first slide.
I think we have time to, we have 7 minutes till the break. So,
how many?
7.
7, okay, yeah.
So what we can do is
play the video.
we can play the video, which is 12 minutes. So you're going to sacrifice
Yeah.
3-4 minutes from your break, okay?
And when we'll be back, so we have some slides in order to provide some steps how you can build in using Python a simple neural network, and we'll have the lab exercise as well.
I wanted to add something here. According to the hidden layer, if we don't have a hidden layer, we can learn only a linear function or function without points. With one hidden layer, breaking points. With one hidden layers, we can learn functions with one breaking points, and with more hidden layers, more complex functions.
Non-linear.
Because
Non-linear. So it's,
non-linear.
what is break? I missed
That
that.
are not continuous, I don't know how it is. That goes here and then here.
Yeah.
Yes, with one. Breaking sinon, tipico cookie.
Okay.
Yeah.
Yeah.
According to the hidden layers.
Yes.
With one hidden layer, we can model every kind of function that has one kind of this point.
Okay.
Yes. And with two hidden
Yes.
Because in the first hidden layer, we learn the features, and then in the second layer, the relationship between the features, and then in the third and last layer, the complex statistics.
Yes, patterns. Yes.
Yes,
So
patterns.
the more complex the model becomes,
More
the
layers.
yes, the more layers we are adding, the more complex the model becomes, and then actually there is something called distillation process. So we start with the high-level features like number of bedrooms, swimming pool, if we are trying to predict, let's say, the rent of a house, right? But then the model is actually getting into the fine details of those features. As we are adding layers, then those like features become even more fine. They're gonna become distilled, okay, until we make a decision. So we're gonna actually get a nice feeling about what we are just saying now when we're gonna work with convolutional neural networks and see actually what are the features of an image and how do they change from layer to another layer. So for instance, if your task is to predict, I have an image of a cat versus an image of a dog, then the network initially receives features from, let's say, the training data, but then it actually starts finalizing or starts getting features about the way the ears look like, whether there is a mustache, whether, for example, how the mouth is located in the image, and so on. You will actually be able to visualize this. That's why I'm saying that you will get a better feeling tomorrow. Okay? We have 3 minutes. So this is backpropagation, the video for backpropagation. It's a very intuitive way of explaining backpropagation. There are more advanced videos there. Feel free to watch. But this is actually a great way of explaining within 12 minutes.
Here we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last 2 videos, or if you're just jumping in with the appropriate background, you know what a neural network is and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons. And I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2. While the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation, and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a tube. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random. Maybe something like 0.5, 0.8, 0.2, on and on. And we can't directly change those activations. We only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we wanted to classify the image as a tube, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down. We care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of the theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together, wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing the tube get more strongly linked to those firing when thinking about a tube. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. So keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand.
That was it, so the rest is a little irrelevant, but that links pretty nice with the backpropagation that we mentioned. And one key takeaway from this video is that you have the input data, which we're going to see in the next set of slides after the break, but there is an output which you saw with value 0.2 and blah, 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 blah. Okay, so what are those outputs? These are just probability values. And this 0.2 actually tells you that the training point, which shows you the digit number 2, has 20% probability to be recognized as a digit number 2. Okay? And what the purpose of this is actually to get training data, adjust the weights through backpropagation in order the 0.2 to become 0.99. Okay? That is the story. That is all what is happening. And at the end of the day, at the heart of backpropagation, there is something that's called, that we're not going to cover, it's called gradient descent. Remember, we have this complicated surface, and the goal is to actually locate those W's that gives you the minimum value of that surface. Alright? Gradient descent is the algorithm that actually can do that for you. Okay, so let's have a break, and we'll see each other at 4:30.